Hello everyone, the concept that we are going to study today is Vegard's law. But before we move on towards Vegard's law, there is a concept called as lattice parameter that I have covered in my previous video. You should check that out. So starting with Vegard's law, we'll first consider the formula of Vegard's law. What is the formula? It is displayed by equation number A. Now it says at constant temperature, the formula displayed by A is the formula for Vegard's law. In this formula, A naught A is nothing but lattice parameter of pure A. A naught B is lattice parameter of pure B. A and B combine together to form crystal C. Crystal C, so AC would be the lattice parameter of resultant crystal C. Now, as we see, crystal C is formed only out of two components, A and B. So, if the concentration of component B is X, then all the remaining would be the concentration of A, that is 1 minus X. We should note down that this is all at constant temperature. What this law does is it relates the concentration of the components to the change in lattice parameter of the resultant crystal. So this law gives the relation between the concentration of the components and the lattice parameter of the resultant crystal formed out of those components. So let's move ahead and understand this law better by considering two examples. One of the important assumptions of Vegard's law is that the two components that are mixing, that is A and B, should have same crystal structure. So if A is simple cubic, then B would also be simple cubic, and thus resultant C would also be simple cubic. Now to understand this better, let's consider example of Zn Ag. In this example, we have taken 25 degrees Celsius constant temperature since Vegard's law is for constant temperatures. Here we have taken Ag as the solvent and Zn as the solute. Ag has radius 144 picometer while Zn has radius 134 picometer. What we understand is the solute has smaller radius than that of the solvent. What does the solvent-solute combination mean? It means that we have taken pure Ag and we are increasing the percentage of Zn gradually in it. And we are looking at the result of this increase in percentage on the overall lattice parameter of Ag-Zn. So we need to consider the relation between radius and lattice parameter. In our previous video, we saw that the radius and lattice parameter are directly proportional to each other. Thus, since Zn's radius is greater than Ag, the lattice parameter of Zn is smaller than that of Ag. So, we can just conclude in the graph, we see as we increase the percentage of Zn, since the radius is smaller, Zn's lattice parameter is also smaller, so it brings down the overall lattice parameter of Zn Ag. So, from the graph, as we increase the Zn percentage, which has smaller lattice parameter, it brings the overall lattice parameter of Ag-Zn down along with it. From this we can conclude that if the lattice parameter of solvent is greater than that of solute, there is decrease in the lattice parameter of the solution. This can be explained more clearly by a basic diagram. This is not a scientific representation, but just for understanding, just consider that this is a unit cell of Ag and this is a unit cell of Zn. Here we see what happens when Ag, which has larger lattice constant, is combined with Zn, which has a smaller lattice constant. It leads to the formation of Ag-Zn, whose overall size or lattice constant is smaller than that of Ag. So Zn brings down the overall lattice constant or lattice parameter of Ag-Zn, as we saw in the graph. So look at this diagrammatic representation. Here we have got a crystal of Ag. We just took this unit cell and repeated it in 3 directions. So this is our unit cell of Ag. When we add only one unit cell of Zn, there is formation of Ag-Zn whose lattice parameter is smaller than that of Ag. Again, we increase the percentage of Zn. We see decrease in the total lattice parameter of Ag-Zn. And thus we see as percentage of Zn increases, the lattice parameter of Ag(Zn) decreases. Remember, this is not the scientific representation of the crystalline structures of Ag(Zn), but this is for your understanding only. Let's consider one more example which is exactly opposite to the Ag(Zn) example. In Ag(Zn) example, Zn's lattice constant was smaller than that of Ag. That is, solute's lattice constant was smaller than solvent. We saw decrease in total lattice constant of solution. Now let's see another example where exactly opposite case is happening. Let's consider the example of CuZn cube. In CuZn cube, we take copper as the solvent whose radius is 128 picometer, while we take zinc as the solute whose radius is 134 picometer, and of course constant temperature 20 degrees Celsius. Here the case is exactly opposite. In the previous case, what we saw is the radius of the solute was smaller than that of solvent. Here opposite is happening. Radius of the solute is greater than that of solvent. So let's see what happens. As we know, R is directly proportional to A. That is, radius of the molecule is directly proportional to its lattice constant. Thus, lattice constant of copper is smaller than zinc. Since the zinc, that is solute that we are adding, has a larger size, exactly opposite thing would happen, and lattice constant of CuZn cube would increase with increase in atomic percent of Zn. From this we can conclude that if A of solvent, that is lattice parameter of solvent, is smaller than lattice parameter of solute, lattice parameter of the overall solution increases linearly with increase in percentage of increase in percent of solute. So thus we came about two results. The first result was if lattice parameter of solvent greater than solute, decrease in overall lattice parameter of solution, and if lattice parameter of solvent smaller than that of solute, the overall lattice parameter of the solution increases linearly with increase in percentage of solute, and this is at constant temperature. So if asked about the statement of Vegard's law, we can say the lattice parameter of a continuous solid solution varies linearly with the concentration at constant temperature. This is the statement for Vegard's law, but this law is not an exact science. Deviation from Vegard's law is often seen, and the points to be noted in this laws are: this law is applicable only for ionic salts and compounds and substitutional solid solutions. This law often deviates in positive or negative way, so it is not a theorem but just an observation.